Hi there. We're going to work on the molecular shapes progression lab. To work with this, you need either the handout that was given to you by your teacher in class, or you need to print out the document that's associated with this assignment. You'll also need your Plainsman periodic table. I have a copy of that here. In this segment, we're going to work through the columns 1 and 2. So I'm sharing my screen here. The two columns that you need to complete for this assignment are total valence electrons, which is column 1, and then the Lewis dot structure as well. I will do 2 examples, and after I finish the examples, then your task will be to go through and complete all of the other formulas and work through columns 1 and 2 for those formulas and submit pictures of columns 1 and 2 from the front and the back side. In a further or a later video lecture where we will work with columns 3 and 4, which are molecular shape and symmetry, and then later we'll finish out the entire rest of the lab. But for today, or for right now, just columns 1 and 2. Let's start with column 1, total valence electrons. It says that we need to add the total valence electrons for each atom has from the periodic table. So using our periodic table, and as a reminder, we look at the column that each of the individual atoms are in and add up the valence electrons for all the atoms that make up a particular compound. We're going to use or do this for H2O as our first example. That's the example on the front side, and then we'll also use do an example using H2CO on the second side. So for H2O, for column 1, we're going to put together all of the valence electrons. H2O means that we have 2 hydrogens and 1 oxygen. So look up hydrogen on the periodic table. We can see that's in column 1. So that means 1 valence electron for each of the 2 hydrogens. So that will be a total of 2. So we'll take 2 and add to that the number of valence electrons for the 1 oxygen. Now, oxygen is in group 16, which means that there are 6 valence electrons for oxygen. That's also called 6A, so 6 valence electrons. We'll add those and get a total of 8 valence electrons. Okay, so that's how we work column 1 for H2O. You can pause now and work through for each of the other ones on the front side if you like, or we will go on now and work with column 2 for H2O, which is Lewis dot structure. So looking back at the top of our shared screen here, we're going to draw the dot structure of the molecule and include all electrons. So looking at the electrons that we have that were brought to the atom, or sorry, brought to the molecule by the different atoms that make this up. When we work with this, we'll work with 2 different checks. We'll be checking to see if the total valence electrons of the structure that we draw equals the total in column 1. We'll also check each element to make sure it has its octet, which means that it has electron configuration of a noble gas. It can get that by sharing electrons. That will be 8 for pretty much every type of atom except for hydrogen, which will have 2. There's a note here that says 1 molecule has reduced octet exception. So you'll be looking for something from your class notes that can have a reduced octet, and that will be one of the ones that you do on your own. Next, we're going to look at drawing this Lewis structure. Sometimes that's also called a Lewis dot structure, and we'll be using the canvas part of your screen. Let me find that. Looks like I have a whiteboard that I can use, so we'll try working with that. All right, so we are going to use a whiteboard. You could also use your canvas. So we'll start with H2O, and I'll be using a drawing dot and drawing out this, this molecule. So the first thing we want to do is consider the arrangement. Remember in your class notes it says number 1, we arrange the atoms by determining which atom is the most needy. Now, for H2O, that means we have 2 hydrogens and an oxygen. And just a heads up, hydrogen will never be the neediest. It can only be an outer atom. It can't be a central atom. But let's go ahead through those 3 steps, determining which is the most needy. So hydrogen only needs 1 more electron to get to its octet, so it's not going to be the neediest. Oxygen, on the other hand, with its 6 valence electrons, needs an additional 2 electrons, so it's needier than the hydrogens. And of course, whatever atom we have will always be needier than hydrogens. So we're going to put the oxygen in the middle. It'll look like that, okay? And then we are going to, actually we're gonna erase that, undo, and use a draw line. Let's see if we can draw the oxygen. Okay, so there's an oxygen. Yours will probably be better. So it's the central atom. Then we are going to arrange the hydrogens around it. So here's a hydrogen here. Maybe should have used the Canvas apps tool, but that's okay. I'm going to put that hydrogen with a single bond from the oxygen to the hydrogen. I'll put the other hydrogen over here. And this is an example of drawing a Lewis dot structure. And so I've arranged the atoms, put the central atom as oxygen, single bonded the hydrogens to the oxygen. Step 2 is to distribute the electrons. In distributing the electrons, then we need to draw the lone pairs. Each of these hydrogens is actually at its octet because a bond is 2 electrons. So we're not adding any lone pairs ever to hydrogen. However, the oxygen only has 2 from this bond, an additional 2, so a total of 4 with its bonded electrons. So we have to add lone pairs. So let's see if I can do that with this. Here is an electron. Should look more like a dot. In fact, let's go to a dot. And here is an additional electron. There we go. And this constitutes what we call a lone pair. Okay. We need an additional lone pair. There's an electron down here and an electron down here. Okay. All right, so now let's do our checks. I'm going to go back to the screen that we had before and look at the checks just to make sure that you understand what you're looking for. So total valence electrons from this particular diagram must equal the total in column 1. Well, we totaled 8 valence electrons, so we're going to go check that. And then we will also check the second thing, which is the octet. Let me go back to my sharing, to my whiteboard. And we're going to do those 2 checks, okay? So we totaled our valence electrons at 8. So this bond is 2 electrons, so that's 1, 2. This lone pair, 3, 4, 5, 6, and then 7, 8. So our valence electrons do equal the electrons that we have in this electron dot structure. The second thing we check for is our octet. So look at this hydrogen. It is an at octet with 2 electrons that are part of this bond. So this shared set of electrons gives hydrogen its octet. Same thing for this hydrogen. It has an octet because it has 1 bond. That's all that hydrogens will ever have. Now we'll check the oxygen. Oxygen needs 8 for its octet. So we have 2 here, 4, 6, and 8. So we have checks for both of those things. Let's go back to our lab. And we can see now that we need to draw here the oxygen, which is single bonded to 2 hydrogens and has 2 lone pairs of electrons. And that is what you need to do for this Lewis dot structure for H2O. scope. Okay, I have a new screen with the same drawing on it. So this is in Canvas. And I just want to show how you can do the checks. So we check the number of valence electrons as 2, 4, 6, 8. So we can check that. And our octet, remember hydrogen has an octet with 2, just 1 bond. This hydrogen just 2 with 1 bond. And this oxygen has 2, 4, 6, 8 for its octet. So I'm just checking each atom to make sure they have octet, and we're good. Okay, so this is a viable Lewis structure or electron dot structure for this atom. Now we're going to go back to our shapes lab. And remember that you should have drawn in what was in that Canvas part of the program into here. Okay. Now we're going to go to the second side of the lab, and you will be doing the total valence electrons and Lewis dot structures for all of these different things. Let's stop here at H2CO and take a look at the valence electrons. Remember that each hydrogen has 1 valence electron. We just checked the periodic table. It's in group 1. So that means we have a total of 2, or 2 times 1 for that hydrogen. We're going to add to that the number of valence electrons for carbon. So we find carbon here in group 14. And remember that the number of valence electrons is the same as the 1 place. You can also look at group 4A. That tells us that carbon has 4 valence electrons. And now oxygen in group 16, we can see that oxygen has 6 valence electrons. So you're going to do that for each of these different compounds, add together all the valence electrons for each of the atoms. That gives us a total of 12 valence electrons. Write that, 12 valence electrons. Now we're going to look at our Lewis structure, that's column 2. So remember our order of working with this. I'm going to go back to my drawing program. And get a new drawing. Okay. So remember, number 1, we're going to arrange the atoms by determining which is the neediest. Our atoms, of course, are 2 hydrogens. And again, hydrogens with only needing 1 additional electron will not be the neediest. They will be outer atoms when we have a molecule. The next one is carbon. Carbon has 4 valence electrons, so it needs 4 more valence electrons. That's pretty needy. And then the last one is oxygen, which has 6 valence electrons, so it only needs 2 more. That tells us that carbon is the neediest of those. It needs 4 more electrons in order to fill out its octet. So carbon is going to be our central atom, okay? We have carbon then that I'm drawing as the central atom. Boom. And we're going to single bond the other atoms to it. So we've got a single bond to a hydrogen. Another single bond to a hydrogen, so that's C with 2 hydrogens, H2, oops. Okay, second hydrogen. And then we'll also bond it to the oxygen. So this is the beginning part, arranging the atoms. Carbon, which needs the most bonds, goes in the center, and a single bonded to the others. Now we're going to add in those lone pairs to fill out octets, okay, arranging the atom. So this hydrogen with the 1 bond already has its octet, this one as well. Now the carbon needs a total of 8, so we've got 2 here for this bond, 4, 6, so it needs 2 more electrons, so that's 1 lone pair. The oxygen only has 2 valence electrons associated with it, so we're going to add in 6 additional electrons. That means 3 lone pairs of electrons. Okay, those are non-bonding pairs of electrons. All right, now let's consider the checks. I'm going to go back and we'll write out the checks. One is valence electrons, right? Where it is, VAL, E minus. And we know that the valence electrons required for this are the 12 that we came up with that are in column 1. We're also going to check for octet for everything. So we'll start with number of valence electrons. And we're going to count up what we have in this structure to see if this is a viable structure. So remember, every bond is 2 electrons. So this is 2, 4, 6, and then the lone pairs here make 8, 10, 12, and 14 total. When we compare that with the 12 that we came up with in column 1, that doesn't match. So now we get to that part of your class notes where it talks about erase a pair, add a pair to share. So let me tell you what that means, or remind you what that means. That means we determine where we're going to come up with a multiple bond. Hydrogens can't have multiple bonds, so it can't be there. It must be between the carbon and the oxygen. So if this becomes a multiple bond, first we identify that that will be the case, and then we erase a pair on one side of the bond, erase a pair on the other side of the bond, and add the pair to share, which is a bond between the two. So let's go through that. Erase a pair, one on each side of the multiple bond, and then add a pair to share. That will be the double bond now between the carbon and the oxygen. Then we count and compare again. Remember, each bond is 2, so 2, 4. This is one bond, that's 2 additional, so that's 6. And then this is another 2 electrons, that makes 8, 10, and then 12. So valence electrons now are check. Now let's look at our octet. Remember that a hydrogen atom has an octet when it has 2 electrons associated with it, 2 valence electrons, and that is this bond. So the hydrogen gets its octet with the 2 that it shares with carbon, as does this hydrogen. So that's good in terms of its octet. Now let's check the carbon. Carbon needs a full 8 electrons. So we have 2 from this bond, 4, 6, and then 8. So carbon is good as far as its octet. The oxygen now also needs 8. So 2, 4, 6, and 8. So the octets are good here. That means that this is a viable Lewis structure. Now let's go back to our lab and take a look at that. So that structure that I just drew in Canvas should go here. You can also put the checks there if you like, with a carbon in the center, double bonded to an oxygen, single bonded to a hydrogen, and single bonded to another hydrogen. Your task now is to complete columns 1 and 2 only for all of the different formulas and compounds that we have here. These are all molecules, remembering that there is a reduced octet in one of those. Another thing that I'd like you to know is that when we get to these C2H6, C2H4, and C2H2, the carbons will be bonded to each other as central atoms, and then the hydrogens will be distributed evenly bonded to those carbons, okay? And count carefully when you count valence electrons for those, okay? All right, finish up and submit for those 2 columns for this, and then in the next video we'll go through the columns 3 and 4.